All right, so let's take a look at refraction. Refraction is when a wave enters a new medium. So we did the experiment where we took the sine of the angle of incidence, sine of the angle of refraction, plotted it, and then from this we're going to get this equation that we're going to use. So we should have gotten a slope of around 2.4. Sine of the angle of incidence is on the y-axis, sine of the angle of refraction is on the x-axis. Throw it into the y equals mx plus b format. Should have gotten something like that. Now, that 2.4 represents this thing called an index of refraction. This is a number that represents a material. So every transparent material has its own index of refraction. So air has an index of refraction of 1, water is 1.33, a diamond is 2.42. So the material that you were looking at was pretty close to what a diamond is. So an index of refraction is a number that just represents the type of material that it's going through. We're going to use small letter n to represent the index of refraction. So let's substitute it in for our equation. So we'll use small letter n, but we have to also include the material that we started in, which in this case was air. So we get this equation here. Copy this equation into your notes. This is called the Snell's Law equation. There are 4 variables, n1, theta 1, n2, theta 2. So let's figure out what all 4 of these variables represent. On the left side of the equation, this represents the material that you're in. So if we take a look at the ray coming in, the ray is going to come in at a certain angle as measured to the normal. It hits the new material and bends as it comes through that new material. So the N1 represents the material that you start in. Most of the time it's going to be air. Theta 1 is your angle of incidence as measured to the normal. The right side of the equation is the material that you're entering. So N2 represents the material that you're going into. So if we go from air to water, N2 would be the index of water. From a diamond to glass, this would be the index of refraction of the glass. Theta 2 is the angle of refraction. Most of the time, this will be what you calculate. You're going to calculate what theta 2 is. So in a problem, you're going to be given 3 of the variables. Calculate the 4th. You can always assume you start in air unless otherwise told. So as it enters different mediums, it bends differently. So you can see here we have a ray of light coming in at 60 degrees in glass and then coming back out into air. Here we have going into water. So because the indices of refraction are different, the rays behave differently. This is what we're going to be able to calculate. We're going to be able to calculate these numbers. So here are some typical indices of refraction. You don't have to copy these because on your worksheet we give you a table of all the different indices of refraction, but we're just giving you some references. Now the key is, what do these numbers really mean? Well, what it tells you is how much slower the speed of light is in that material rather than in a vacuum. In a couple units previous, we figured out the speed of light in a vacuum was 3 times 10 to the 8th meters per second. So now, when we say the index of refraction of water is 1.33, that means the speed of light in water is 1.33 times slower than it would be in a vacuum. So now we can use that idea and calculate the speed of light in water by taking the speed of light in the vacuum divided by what that index of refraction of water is. So if on my calculator I go 3 times 10 to the 8th divided by 1.33, I get this on my calculator. Make sure you can get this number on your calculator. So do this calculation on your calculator. Hit the pause button and go through and do this. You have to be able to get these numbers on your calculator. So the speed of light in water is 2.3 times 10 to the 8 meters per second. So now let's take a look at an example problem. A ray of light enters the water at an angle of 25 degrees. What's the angle of refraction? So again, we can assume it starts in air and then is going to go into water. So step 1, list what you're given. N1 is 1, theta 1 is 25 degrees, N2 is 1.33, calculate theta 2. So write out your equation, substitute underneath, now plug and chug. Make sure that you can get these numbers on your calculator. So you're going to divide both sides by 1.33, you get this. Now that's what the sine of theta 2 is. We don't care what the sine of the angle is, they want what the actual angle is. So now you have to hit the second button, inverse second sine of this number, and you should get 18.5. Make sure you can get 18.5 on your calculator. If you can't, that should be the first thing that you ask when you walk into your class. Ask your teacher how to go from this step to this step. Okay, so the angle of refraction is 18.5 degrees. Now, let's see if that makes sense. Came in at 25, came out at 18.5. The angle went down. Does that make sense? Well, your index went up. So if the index goes up, angle goes down. Inverse relationship. So that's a reasonable answer. So again, here's our situation. So as light goes from a smaller index to a higher index, this is just like what we did in our problem. The light ray slows down and bends towards the normal. So that means that that angle of refraction is going to be less than the angle of incidence. So it's an inverse relationship between index of refraction and the angle. So if the index goes up, so if N2 is larger than N1, the angle of refraction goes down. So in our example, so we go from N1 to be 1 to 1.33, then the angle goes from 25 to 18.5, inverse relationship. Just the opposite occurs if we go from a high index to a low index. What about if we're underwater looking out into the air? Well, we're going from a high index to a low index, 1.33 to 1. That ray of light bends away from the normal. It speeds up.